Dear friends, students and learners, I am Dr. Shashank Shrivastava from the School of Engineering and Technology, Indira Gandhi National Open University. So we were discussing about the course Material Science, and in that I was discussing with you mechanical properties of materials. So today we shall be discussing hardness. What is hardness? So there are certain points which I am mentioning to you. Please listen carefully. It seems that it is easy to differentiate a hard and soft material by bare eyes, but in reality it is very difficult to define the term. What is the reason behind that? It is difficult to correlate the property with stress or strain. This hardness property is very difficult to correlate with stress or strain. And now the general definition I am giving you about the hardness. It is resistance to permanent plastic deformation. It's a general definition, and the engineering definition is that it is resistance to indentation or scratching. Like if you are scratching, like if I scratch my hand, so this is related to hardness. Then it is the ability of the material to resist abrasion, cutting or penetration, and we know that this is attributed to hardness. All these things, abrasion, cutting, like we also get abrasions or bruises in our bodies, so similar to that. And conforming to the above definition, there are two methods of hardness measurement. One is scratch hardness and the other one is indentation hardness. So when we talk about hardness, we have known the definition of hardness. So now we move on to how we will know how hard a material is. So there are two methods. One is a scratch hardness, the other one is indentation hardness. So now we discuss the scratch hardness. The scratch hardness is commonly measured by a test known as Mohs test. It was invented by the scientist. So this method is based upon the scale of hardness known as Mohs scale. So he made a scale for that. How hard a material will be, it will be given by that scale. And there are 10 standard minerals which are arranged in the order of their ability of hardness, and they have to be scratched. In that way, we get to know about the hardness in this particular Mohs test. So continuing with that, the softest mineral with a scratch hardness of 1 is said to be talc. Like talc, what is talc? Like we have talc powder, you must have seen. People apply it on their faces now. And whereas the hardest mineral, what it is known to be, it is diamond. And it has a hardness of 10 on the Mohs scale. So talc has hardness of 1 on the hardness scale, and this diamond has 10 on the Mohs scale. And the other minerals which come in between 1 and 10 are given in this increasing order of hardness. I am listing it here: gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, sapphire and corundum. So then we compare a scratch on the material surface, which is produced under standardized conditions, with the scratch on one of the minerals occupying position from 1 to 10 on Mohs scale. This is the procedure. Although the test had been chiefly designed for minerals, we can also do it for metals. Metals can also be tested by this method. So mostly metals fall in the Mohs hardest range of 4 to 18. And it is very difficult to differentiate between two metals whose hardness are very close. And that is the reason why this method is not that well suited for metals. Because if suppose the hardness of two metals is very close, then Mohs scale cannot tell about it. So we are not using this for metals as such. So from the scratch hardness, we move on to the indentation hardness. Most widely used method it is, and it is acceptable method of hardness measurement. We have seen that there are several parts of machines and structures. Like we have the gears, we have the axles in our vehicles, the rails. Those are subjected to service requirements where high resistance to indentation or abrasion is required. So this method, the indentation hardness method, uses an indenter of a specified material, shape and size, which is pushed against the material surface under a specified condition of loading to create an indentation. So there is a certain material of a definite shape and size which is used to push against the given specimen. The dimensions of indentation are then used to designate the hardness of the material. So when I push this indenter onto the specimen, then it will create a certain scratch or some symbol will be there. So that will be used to measure or designate the hardness of the material. So the first kind of hardness test that we are now going to discuss is the Brinell hardness test, and in this method we use a steel ball of 10 millimeter diameter as indenter. So a ball is used here and its diameter is standardized, which is 10 millimeter. So this indenter is first placed on the surface whose hardness is to be measured, like it is shown in the diagram. This indenter is placed on the surface of the specimen. Then load is applied on this indenter, and when this load is further removed, then what happens? An indentation is created on the specimen surface. So the difference between the harder material and the softer material as per this Brinell hardness test is like this. In case of harder material, we can apply a load of around 3000 kg force, whereas in case of softer material we can apply a load of 500 kg force only. In a harder material, tungsten carbide indenter is used, whereas in a softer material, a steel indenter is used. And in a harder material, load is applied for 30 seconds, and in softer material the load is also applied for 30 seconds. So this is the only similarity, that the load is applied for the similar time. So now we get the formula for that. This is known as Brinell hardness number, BHN. How do we get it? Here it is given. Suppose P is the load which is applied on the ball, indenter ball, and then the indenter ball pushes against the surface of the specimen and creates an indentation. So P is the applied load, D is the diameter of the ball in millimeter, and small d is the diameter of the indentation in millimeter. So BHN is given by then P, that is the applied load, divided by pi d by 2 into d minus root d square minus small d square. So this is the formula for BHN. So how we get this formula? Let's see in this derivation. You can see the circular thing which has indented on the specimen surface. You can see in the figure. So the diameter of the circle is big D. This is the diameter of the indenter. Small d is the diameter of the indentation, and h is the thickness of the indentation. So BHN is given by P divided by surface area of indentation. So that means it is P divided by pi into D into H. So here one assumption is taken that small d is very close to larger d. So we take here the larger d. So H is then given by, if you can see in the figure, here by Pythagoras theorem we will find out, and H is simply capital D by 2 minus OB. O is the center of the circle and B is the point where it is cutting the chord of the indenter ball. So from this triangle, what we get by Pythagoras theorem, OB is equal to root capital D by 2 square minus small d by 2 square. That means root OA square minus OB square by AB square. So finally we get from this that H is equal to D by 2 minus capital D by 2 square minus small d by 2 square. So substituting this, we will get BHN as P, that is load, divided by pi capital D by 2 bracket open capital D minus root of capital D square minus small d square. So this is the way how we derive the Brinell hardness number. And this BHN or Brinell hardness number is given in units kg force per millimeter square. So it is quite similar to our stress or pressure unit. BHN does not convey any physical meaning as such, because the load P is not uniformly distributed over the indented surface. So this load is not completely distributed uniformly over the indented surface, so it has not got any such physical meaning. And BHN value obtained for a material is fairly reproducible provided the load P and diameter D are same for each test. So this BHN value can be got again and again if the load and diameter are the same for each test. So to obtain the same BHN at any other load, what we need to do? The ratio of a small d to capital D must be constant. So from the formula, what does that mean? It means that the capital P divided by capital D must be constant. That is, load divided by the diameter of the indenter ball must be constant. The calculated value of BHN may be slightly in error because of the assumption, like I told you earlier, that the diameter of the indented surface is same as that of the indenter, which is not exactly true. We take it as an assumption that the diameter of the ball and the diameter of the indented surface, that is capital D, is equal to small d, which is not exactly true. Why? Because after the removal of the load, some elastic recovery takes place. So certain strain is recovered. Like we did in our previous lectures, we studied about elasticity. So that phenomena is happening here, whereby the final diameter of the surface becomes different than the ball diameter. And for harder materials, elastic recovery is greater than for the softer materials, obviously, because softer materials have a tendency to be in plastic mode. So recovery for them is not as good as the harder materials. There are certain anomalies in this test, like one is an anomaly that arises is measurement of the diameter of indentation diameter small d due to localized deformation of metal in the region of indentation. So here is a figure which shows that the cross section through indentation in a cold work metal. So we see here that because such a metal has a little capacity to strain harden, the metal has a tendency to pile up along the edge of impression. You can see in the figure it is piling up at the edge. So this behavior is known as the piling up or ridging. So that because of this ridging or piling up, this indentation diameter is different than what we perceive. So another phenomena is there, like piling we study. So here another phenomena is here, sinking in is there. So sinking in of an annealed metal. Annealing is a process, heat treatment process. So due to that, sinking in happens. The depression around the edge of the metal will apparently increase the diameter of the impression. So again the diameter is varying. To arrive at the true value of a small d, the indenter is often coated by a dye before making the indentation. What happens due to this coating? The diameter then can be measured on the colored ring. Similarly, in case of a plate specimen, it should be ensured that there is no interference between the indentation and the edge of the specimen and the interference between two indentations. Suppose there is a triangular piece and the indentation has taken place at a certain point, but it is too near to the edge of the rectangular piece. Then what will happen? Both will mix up. Similarly, there are two indentations on that surface and they are very close to each other. So what will happen? They will cut each other. So we will not get a fair idea. That's why it is mentioned here. For this reason, it is advisable that the center of indentation should be at least 1.5 into capital D away from any edge. So that is a standard distance from the edge of the specimen. It should be maintained. Same distance should be maintained between two neighboring indentations. So there are two neighboring indentations, then we also need a distance of at least 1.5 into capital D. Also, the thickness of the plate must be at least equal to the diameter of indenter so that the plastically deformed zone below the indentation does not interfere with the back surface. So if suppose the material is very thin, what will happen? Your indentation will go through the material. So there is no use then. So next test is the Rockwell hardness test, and this one is quite famous in case of hardness testing and very popular. So in this case, what is there? The tools, two types of indenters are there. A braille indenter in form of 120-degree diamond cone. So this is one type. The second one is the steel balls, and they may be of diameter 1/8 inch or 1/16 inch. So Rockwell hardness method is different from the Brenner method as it is not measured as ratio of load to indentation surface area. So in case of Brenner hardness, what we were doing, we were applying a load and indentation was created on the surface. But in the case of Rockwell hardness, this thing is not there. Then what is there as such? Instead, it is measured on an arbitrary scale on which hardness number is inversely proportional to depth of indentation. So simply it is measured by the depth of the indentation. So the procedure for this test, Rockwell hardness test, first place the specimen on the platform of the machine, then apply a minor load of 10 kg force. So this load is not like that in case of the Brinell hardness. It's a minor load that is applied to the indenter, and why it is applied? This helps to seat the specimen and reduces the tendency of ridging or sinking in. Like we studied the ridging and the sinking in the previous case of Brinell hardness. So here also it happens. So to avoid those things, what we are doing, we are simply applying a minor load which will help the indenter to sit on the specimen in a nice manner. Thereafter we applied a major load which could be either 150, 100 or 60 kg force. Now after applying load, it is left as such, then depth of indentation is automatically recorded as hardness number on a dial gauge. We use a dial gauge which is generally used for surface smoothness measurement and surface roughness, all those things. So here also it is used. So the dial of the gauge is divided into 100 divisions, with each division representing a penetration of 0.002 millimeter. So 0.002 millimeter represents one division, and there are 100 such divisions. The dial scale is reversed so that a small indentation depth is read as high hardness. One combination of load and indenter will not be able to provide a wide range of hardness. So it is not possible that if we are just simply using one load and one indenter, it will give us a range of hardness. So for that purpose, what we will do, we will have different combinations. Loads with 3 indenters are used in different combinations to provide wide range of measure of hardness of several materials. So this table shows the different scales of Rockwell hardness, which is often expressed as R. Rockwell, so we take R from that, with a suffix to indicate the scale, which scale we are using. So you here in the table you can see A, C and D, 3 scales are given, and loads are accordingly given. For the A1 it is 60 kg force, for the C1 it is 150 kg force, for the D1 it is 100 kg force, and the hardness there, the range is given 100 to 500 into D. D is the depth of the indentation, and generally the scale RC is very commonly used for steel. So what are the advantages of this Rockwell test over the Brinell hardness test? So here are some of them. It can be performed on very small parts in finished or unfinished condition. So both things are there. It can be in finished or in unfinished condition, and very small parts can be tested also. Since the indentation is very small, the finished surface is not spoiled, and unfinished surface does not affect the indentation. Besides this, no measurement of indentation and consequent calculation are needed. Thus the method is direct, fast and free from personal error. Like in the previous one, we saw that we have to do the calculations and we have to derive the Brinell hardness number. So it is not here. So it's a much better process. So now a certain number of precautions which we should take before doing the Rockwell hardness test. The first one, thickness of the plate specimen must be at least 10 times the depth of indentation. Like I earlier also mentioned that the thickness should be such that the indenter should not go through it. So it should be at least 10 times more than the depth which is being created in the specimen. This will avoid any effect of indentation to pass through the thickness. Second one, the distance between two adjacent impressions should at least be 3 times the size of indentation. So again the thing which I have explained before, that if there are 2 indentations, then the distance between these 2 impressions should be at least 3 times the size of the indentation. Suppose there is one indentation at point A and there is one indentation at point B. So the distance between them should be 3 times the dia of that particular indentation. Third point, the hardness read from indenting the curved surface should be corrected for curvature. If any curvature is occurring, then we should correct it for that. Fourth point is that surface on which indentation is made must be clean and smooth. So cleanliness and smoothness of the surface should be there, and it should be well seated upon a clean platform. The last point that is here, the rate of load application is controlled in Rockwell hardness testing machine, and it is achieved by a dashpot adjustment corresponding to a standard rate of loading. So till now we have discussed the Brinell hardness and the Rockwell hardness test. Now further we discuss the Vickers hardness test. So Vickers hardness number is defined as the ratio of load P to the surface area of the indentation. It is quite similar to the Brinell one. The Vickers indenter is a diamond pyramid. So here's the difference from the Brinell one, whether we were using a ball, a steel ball. Here it is of a different shape. It is a diamond pyramid with a square base, and included angle between the opposite faces is 136 degree as given in this figure. The impression of this indenter has a square boundary with depression inside. So you can see there is a square cross section. This is the square boundary and it is a depression inside. So here also one formula is there. The lengths of the two diagonals which of the square you were seeing are measured under microscope, and average is used to calculate the surface area of the indentation. So the formula is given here and you try to prove it by yourself, and if it is not possible for you then you can later discuss with me. So VHN is given as 2p sine theta by 2 divided by small d square plus 1.854 into p by small d square. So what are the symbols here? The p is the indenting load in kg force, d is the average of the two diagonals. See, there were two diagonals you saw in that diamond pyramid indenter, and theta is the angle between opposite faces of diamond cone, which is 136 degree as shown in the earlier figure. The impression of the diamond cone is a square under any load. So if you are applying any kind of load, the impression will always be square type. Hence the impressions are geometrically similar irrespective of the load. So this provides a very good sophistication for us. This provides a great convenience of a continuous scale from very soft material to very hard material without changing the load or indenter. So here we see that it's a continuous scale. Like in case of Rockwell, it was not there. Different kinds of scales were there. But here we see that we can be continuous while measuring from a very soft material and going to a very hard material. Generally, for a given load, hardness from 5 to 1500 VHN can be measured with the Vickers indenter, and it makes VHN, that is Vickers hardness number, independent of load except at very high loads. So leaving aside the very high loads, we can measure hardness for any other kind of load and in a continuous manner in this Vickers hardness test. However, loads between 1 kg force to 120 kg force are commonly used for VHN measurement for very soft to very hard metals. So for metals, from very soft metals to very hard metals, we are using a load of 1 kg force to about 120 kg force. For the reason of independence of VHN of load, this method has been widely accepted as a research tool. So as earlier told, various kinds of loads in this method can be used and in a continuous manner. So it's a very good point and it can be used as a research tool. Now some shortcomings of the Vickers hardness test. Vickers hardness measurement cannot be made on poorly finished surface. So that means we need a very good finish on the surface for Vickers hardness measurement. An element of personal error is introduced because of inaccurate measurement of the diagonal of indentation. So as you saw in that square, diagonals were there. So it is possible that we don't measure the diagonal in a proper manner, or if it is measured then the dimension is wrong. So that's an element of personal error. Then again, the anomalies of ridging, like in the case of Brinell, were there. So in case of cold work metals, this ridging happens and sinking happens. In case of the annealed metals, like we discussed earlier. So these are some of the shortcomings, and it is observed in Vickers impression similar as in case of the Brinell indentation. Then the barrel shape of indentation causes an apparent increase in hardness due to ridging. Pin cushion shape of indentation causes an apparent decrease in VHN due to sinking. So these two things are shown in the figure. See the first one, the first figure is a perfect indentation of a diamond pyramid. The second one is the barrel shaped impression. Why it is happening? Because piling up is there, ridging is there at the corners, and then the pin cushion one is there, which is sinking. So these two are the defects, and the first one was the correct one. After discussing the three types of test, hardness test, Brinell and then Rockwell and then Vickers, further we discuss one more kind, that is IGNOU hardness test, and this one is quite frequently required to determine the hardness over a very small region or a very small part. So suppose we have a very small specimen of small dimensions, then here IGNOU hardness comes handy, and examples are there, like delegate gear of a watch. So in a watch, a gear is very small. Then area where sharp hardness gradient exists, there also we can use. So solution to such a problem may be using a very small indenter under a small load. So like earlier we had used larger loads and larger indenters, so in noob hardness we only use a small indenters under a small load. The figure is also given here. Again, diamond shape you can see. A diamond indenter having pyramidal faces with very large included angle is used. So angle included is very large, but the indenter itself is small. The indenter is pressed against a metallographically finished surface, so finish also should be very good, to produce an indentation of the diamond shape. Again, the diamond shape is here also. Longer diamond of the impression is approximately 7 times the shorter diagonal. So in this case we see that the two diagonals there are of unequal length, so the larger one is 7 times that of the shorter one. The depth of indentation is about 1/13 of the longer diagonal. The noob hardness number is the measure of the ratio of load to projected area of impression, like we have seen earlier also in case of Brennan and all. So it is given by P by D square into C. So P is the load, D is the length of the longer diagonal, and C is a factor of diagonal pyramid supplied by the manufacturer. The indentation load here is very small, often as low as 30 grams. So earlier we were seeing it was about 100 kg force, 150 kg force, now it is only 30 grams. The small impression is measured under the microscope. Since it is very small, we need a microscope. Since the area over which the hardness measurement is made is very small, KHN is sometimes called the micro hardness as well. It is highly essential that the surface of sample must have metallographic finish. Very good type of finish, like a metal, shining metal should be there. Any error in the measurement of diagonal length small d can cause error in the hardness. So again, this precaution is very much needed. Error in locating ends of the impression becomes larger at lower load. Conclusion is that hardness has a tendency to increase with reduction in load, and corrections for such error are also available. So there is one more method, the Martel method. So in this, what we do, we measure the dynamic hardness. Dynamic hardness of a material is measured by dropping a small weight from a fixed height on the surface of the sample and measuring its height of rebound. So earlier we can say we were doing a kind of a static hardness measure. Now we are doing dynamic hardness because we are releasing the weight from a certain height. Earlier we were just bringing it, the load, slowly, gradually, and placing it on the specimen. The instrument in which this measurement is made is known as the Shore stereoscope. Yet another method of dynamic hardness measurement was developed by Martel thus. He used a pyramidal indenter upon which a ram falls to produce an indentation of the sample surface under dynamic loading conditions. So pyramidal indenter is again here, and the load is a ram which falls onto the specimen. So this one is given as MHN and it is given as WH by V. W is the weight of the falling ram, or then H is height of the fall, and V is the volume of indentation. So you can see here it is somewhat energy per unit volume, because WH represents energy and V is the volume. Further, there is one more method, that is Rattler method. So it is used for the paving materials, like we have seen pavements in our cities and roads, we see pavements. So it is used for that purpose. These kind of materials and the hardness for these materials are measured by the Rattler method. So in this method, what is employed? A wear and abrasion of samples is measured. A number of pre-weighed pieces of concentrate aggregate of bricks are placed in drum, which is subsequently rotated for a fixed number of cycles. Like you have a small stone, so similarly small bricks are placed together in a drum and they are rotated by a fixed number of cycles. Like suppose say 50 cycles or 100 cycles, like that, we fix the number. And due to this rotation or the tumbling in the drum, the sample pieces will wear and will lose weight. So the percentage loss of weight is then used as a measure of wear or abrasion hardness. So you had that bricks, and when it is rotated or tumbled, then it loses its weight, and this gives us the hardness measurement. This is known as the Rattler method. So now we see, after discussing these kind of methods, what is the relationship between the hardness and other properties. So the property of hardness is related to the binding forces between atoms and molecules. The hardness, like other strength, increase with binding forces. So if the molecules inside the material, they are coming together, they are compact, then the hardness increases, and if they are not so, then the hardness decreases. The molecular solids like plastics are soft and have low strength, while metallic and ionic solids are harder and stronger. The covalent solids are the hardest. Diamond is the well-known hardest solid. It has got the covalent bonding. So diamond is the hardest because of the covalent bonding. So this hardness depends on the different kinds of bondings also, ionic, covalent, etc. The dependence of both strength and hardness on the binding forces between atoms and will certainly correlate the strength and hardness. So this molecular compactness between the atoms will help us to correlate the strength and the hardness. Mechanism of indentation is quite complex and involves such factors as triaxial stress, state, friction, strain hardening and creep. So this indentation is quite complex, this hardness measurement, because it involves these factors: triaxial state, stress, friction, strain hardening and creep. It is not theoretically possible to correlate hardness with properties of strength, friction and creep. However, attempts have been made to produce closely approximated relations, and one such between hardness and ultimate tensile strength is that the ultimate tensile strength equals 3.4 Bhn in Newton per millimeter square. So Brinell hardness is there, Brinell hardness number, and it is 3.4 times of that. So there is a figure here. You can see the different kinds of hardness measurement scale is given, and ultimate tensile strength is given on the x-axis. So how they are related, you can see the Brinell one is almost a straight line, others are curved type, Rockwell and this Vickers one. So this is a kind of a method where we try to relate the two, the ultimate tensile strength and the Rockwell hardness, or the Brinell hardness, or the Vickers hardness. Similar relationship exists for different materials, but they will be different than the ones shown in the figure. So finally, what is the use of this hardness property? The use is that the techniques used for improving the material strength, like the heat treatment, mechanical treatments, like we discussed earlier, annealing and all those things, and strain hardening or alloying, also result in the increase in the hardness. So hardness is a kind of measurement for these techniques, whether the material is improving or its strength is going down. So all these things can be detected by the means of this hardness. So hardness check of specimens is the quick and easy method of ascertaining the success of such kind of treatment, heat treatment or any other kind of mechanical treatment. Hardness test is most widely used for all manufacturing operations as a measure of uniformity and quality. So in this session we discussed about the hardness, different types of hardness test, and finally the usefulness of the hardness property, and further we will discuss in the next lessons the upcoming things. Thank you very much.